Okay, welcome back. Let's continue with the tutorial, and I'll just share my screen again. Okay, so we left at this point here. So I'm not going to go through all of this. This was done in the Efficient Engineer video that's in the pre-tutorial material. And yeah, so this PDF is available on that same page where the video was. Please don't further distribute these PDFs. I've paid for, I'm a Patreon of the Efficient Engineer, and I've paid to be a patron and got his permission to share these slides with my students. So yeah, don't just share them with other people. All right, so as I said, I'm not going to go through this as it is here, because the Efficient Engineer's done a much better job of it than I will do. But what I'm going to do is to make use of it in an example. So, and what we're going to do is to make use of some of the FEA results that I've obtained from my SolidWorks simulation model and use those to as the inputs to the stress transformation and more circle example problems, and see if we can get our more circle transformations to correlate with our FEA results. So let's jump to that. So what have I done here? So node 54, let's just go back here and see node 54, which is, which one is it here? Node 54, just one down here. All right, so I've taken a point where somewhere on the side of this beam, where we've got both normal stress due to bending, and I've used X so it correlates with or corresponds to the SolidWorks coordinates rather than the theoretical coordinates that we're using from the MOT example. And we've got shear stress. All right, so remember talking about how to calculate the transverse shear, maximum at the neutral axis up to 0 at the top. All right, so we're going to start with this one. All right, so typical textbook problem on doing more circle, 2D more circle, will say, here's some stresses on a 2D plane, stress element, find the principal stresses and the maximum shear stress, the principal orientations, and so on. Okay, so this is what we have, and I've drawn it as a 3D element because I'm going to include in this the overall 3D more circle at the same time, or not at the same time, but as part of the solution. All right, so to draw more circle, we look at the pairs of stresses on the faces in the X and Y, in this case, directions, right? In the MOT example, it would be Z and Y. So you need to be able to convert from X and Y to Z and Y and so on, and to be able to understand how to do the more circle if you've got different axes than X and Y. Anyway, we're going to use this. I might grab my pencil here for this little bit of exercise. Pen, right? Where is it? There it is. So we need this pair of stresses and this pair of stresses. So basically what we're doing is we're going to plot a point with some coordinates. So, you know, if we want to plot a point on a chart, we need its coordinate in a horizontal direction and we need its coordinate in the vertical direction. And then we're going to put another point somewhere, and we'll need two values, right? The horizontal coordinate and the vertical coordinate. So basically we're just doing high school maths, right? Plotting points and then drawing lines between points. Where's the middle of that line? it crosses at there, and when you're going to draw a circle through, that's not very good, right? Through those points. And we're going to use trigonometry to find some things about this circle. Right? But instead of just numbers that kind of meaningless in just a simple maths problem, here the context is stress analysis and understanding transformation of stress and using this simple high school maths to do that. Right? So let me get rid of, see if I can get rid of all that stuff. And here, pen, erase all the ink. Right. So if we got these two, or these two stresses here, right, to plot a point, we need the horizontal ordinate or coordinate. So that's 35.6. So this point we're going to draw is somewhere along this vertical line. Okay. And then we have this other pair. Its point is going to be somewhere along this vertical line, right? So stress y is minus 0.3. Okay. So somewhere along there is where we need to plot the other point. So before we get there, right, the average stress we can take from those two values, just stress x plus stress y over 2 gives us the average, right? And that will be halfway between those two lines. Then to get our vertical ordinate of our point, so remember, to plot a point, we need two values, and the vertical value is the shear stress. Okay, but we've only got one value for the shear stress, 4.3. What did I say? I said it was negative on the previous page, right? So, and SolidWorks says it's negative. But the easiest, probably the easier way to do this, and the way the efficient engineer does, is to look at each of the shear stresses. So the shear stress associated with the x-axis stress, which way is it tending to rotate the element? Right? Tends to rotate that element clockwise. Okay. And he says that you plot clockwise above the horizontal axis. Okay. Or he says that clockwise is negative, and negative is the goes upwards on our axes, and positive goes downwards. So this is opposite to MOT. So this is where it gets confusing, right? And you need to be careful who you follow, right? So as I said, I'm following the engineers, the efficient engineer, and what's in that PDF of his that I've provided for you, right? So kind of I guess a simpler way to deal with it and make sure you get the right answer is to not worry about positive and negative, and just remember clockwise is plotted above, counterclockwise is plotted below. Okay, so here clockwise is plotted above. And then the other one, right, for the stress, normal stress in the y direction, its accompanying shear stress is tending to rotate the element in an anti-clockwise direction. So anti-clockwise or counterclockwise is plotted below. Right, so that's plotted down here. So that's the hardest part. Right? Now we've just got 2 points. Draw a line between them where it crosses the horizontal axis. Because we're the same distance above and below, that's going to cross at the middle of the line. That's going to be the center of the circle. The line from here to here is the radius. We've got a little triangle here that we can use for Pythagoras to do our calculations. So, so the order I've done it here is to work out the radius, and it's just the square root of the sum of the squares of the sides. Right, so the length of this bottom side here is stress x minus the average stress, all squared, plus the shear stress, all squared, the square root of that. Okay, square root. Yep, so just Pythagoras, that's all it is. And we get the radius is 18.46. Then we can draw in the circle, which is known as Moore's circle. And the extremities of this circle give us the maximum and minimum stresses. Okay, so in the horizontal direction, stress max is the extremity out here. Stress minimum is the extremity out to the left. Right, so we can put that in and do the maths. Stress average plus the radius gets us out to stress maximum. Stress average minus the radius gets us out to stress minimum. Okay. And the maximum shear stress is the height of the circle. Right? So that goes across there. The maximum shear stress is just the radius. So we can calculate that and get 18.46 megapascals. The other thing that we can get from here, well, firstly, this line that we've drawn originally, that represents the state of stress in this orientation that I've got up here. Okay, so I might get rid of my pen now and use the laser pointer. So this line here, or this orientation of this diametral line here, represents the state of stress in this orientation of the coordinate system. If we rotate those coordinate systems right to any other angle, the components of stress will change. Okay. And when we rotate this around to horizontal, right, that gives us the orientation for our principal stresses, our maximum and minimum normal stresses. Okay. So we can look at this angle in here. Well, firstly, the angle between X and Y axis on Moore's circle is 180 degrees, right? But on our actual coordinate system on our element, it's 90 degrees. Right? So what we see on Moore's circle is twice the actual rotation. Right? So here we've got 2 theta p. So once we've established that, we can do some maths, trigonometry, to work out the angle theta p, and it's just half of the inverse tan of opposite over adjacent. Okay, and we get our angle 6.7 degrees. So this angle on here is going to be what, about 13.4 degrees, but our actual rotation of our element will be half that, which is 6.74 degrees. Okay, and we rotate our coordinate system in the same direction as we go on our Moore's circle. So we go from X clockwise around to the maximum principal stress axis. We do the same thing with our element here. So that's in 2 dimensions. So we can do the same thing to rotate here to get to the maximum shear stress orientation. And if we do that, what do you see that we get for the normal stresses in that orientation? Okay, we'll see that the stresses in the new X and Y orientations will be equal to the average normal stress. Okay, now the 3D Moore's circle, we look at this face out here. So in this case, the Z axis. And we can see that there's no shear stresses on here. So this is also a principal stress. So just going back a step, in the orientation where we have maximum normal stress or the principal stresses, what's the shear stress in that orientation? Okay, it's 0, isn't it? Okay, so on the principal planes, we have 0 shear stress. So that tells us that this plane out here is also a principal plane. So knowing that, we can say also that the normal stress in this direction is 0. It's just a free surface. So we can plot that point or that normal stress here on the horizontal axis. Then once we've done that, we can draw two more circles, two Mohr's circles, right? One between stress 2 and stress 3, and another one between stress 1 and stress 2. Okay, so overall maximum stress is 36.1. Overall minimum stress is stress 3, which we calculated before, and we have this intermediate stress here, which is 0. And in this case, the maximum absolute shear stress is stress 1 minus stress 3, which in this case happens to be the same as the in-plane maximum shear stress. Now, that's not always the case. So there will be times where stress 1 or stress max and stress min, as we calculated in the 2D problem, are all positive or both negative. Right? And in this case, and in that case, the maximum shear stress will be greater than the in-plane shear stress. Okay. Right. So that's all well and good, but the most important, well, not the most important thing, but important thing that we need to do from here in terms of design is to work out, well, what's our factor of safety with these stresses? So we've worked out what the maximum stress is. We know what the maximum shear stress is. How do we make use of that in design? Right? So we need to compare this with the yield stress, but we can't directly just compare our maximum principal stress with the yield stress. We can't compare the maximum shear stress directly with the yield stress. We have to make use of failure criteria, okay, which is covered in the pre-tutorial videos. Right, so there's two criteria that we discussed. Firstly was the Tresca criterion, which said that the maximum shear stress at yield is equal to the yield stress divided by 2. Okay, and if we compare that with the maximum shear stress as calculated using Mohr's circle, like this, that will give us the factor of safety. All right, so for this problem, what have we got? We've got 434 divided by 2, and the maximum shear stress was 18.5, so that gives us a factor of safety of 11.7. If we use the von Mises criterion, or the maximum distortion energy criterion, that allows us to compare the von Mises stress as calculated from these values with the yield stress. Okay, and the von Mises stress is given by this formula here, which is those principal stresses that we just calculated. Right, so if we do that, sorry, just my animations are a bit out of whack because I move things around. All right, so just going back a step, my factor of safety is greater than 1, so therefore, according to this criteria, we've not yet reached the yield point. Okay, so the von Mises stress, if we put in our principal values that we calculated on the previous page, we get the von Mises stress is 36.5, and our factor of safety is 11.9, similar to what we had for the Tresca, a little bit different, but still much greater than 1. So also predicts that this point has not yet reached the yield point. And if we plot that on this diagrammatic representation of the maximum distortion energy and the maximum shear stress, we can see that we get this point here, right? So along these axes, so they've got the maximum principal stress along the horizontal axis, and the vertical axis is the minimum principal stress. And if we plot that, those here, so previously we had, let's go back to our prev here, we had 36.1 positive for the maximum and minus 0.81 for the minimum. Right, so along here, 36.1 positive for the maximum and 0.81 negative for the minimum. Right, so that lands us about here. So we're a long way inside the locus of failure for both criteria. And it can be seen, maybe. They're both very similar, but because the factor of safety is less than the factor of safety for the von Mises stress, Troska says we're closer to yield than von Mises does, right? So that means we're being more conservative. Okay. Another example. So here, right, so you should have if we're in the tutorial, let's say you have a go at doing this one. So stop the video, have a go at doing the Morse circle for this state of stress. Okay, so you come back. So on the right hand, on the X face, we've got stress in the X direction is 180.2. Where do we plot that on the vertical axis? There's no shear stress. And in the Y direction, we've got no normal stress and no shear stress. But before we get to the shear stress, the average is 90.1. Oops. 180.2 divided by, or plus 0 divided by 2 gives us that. So our 2 points on the chart are given by 180.2 and 0 and 0, 0. Right? So just think, all you're doing is plotting 2 points on a chart. So point X is 180, 0, goes there. Point 2 is 0, 0, right? Goes there at the origin. Okay, so in this case, our stresses are in the principal orientation, right? But we can still go through the process of creating the Morse circle. Right? Radius stress X minus average. Right? Shear stress is 0, so there's no triangle, right, to work with in this case, but you can put in the numbers into that Pythagoras anyway, or you can just work directly from the Morse circle. Tau max is the top of the circle, the extremity of the circle in the vertical axis. Right, so just the radius, 90.1, and the principal plane, or the principal angle is 0. Right? This is the principal stress. Stress max and stress min are the extremities of the circle in 3D. We've got the z-axis here, again 0, so that point is there. So the other two circles are actually just a dot, right? Or in fact, one's a dot and the other circle is over the top of the original one, right? So the circle between stress min and stress z is a dot, and the circle between stress z and stress max goes over the top of the circle between stress min and stress max. All right. And plotting on Morse, using the failure criteria again. Maximum shear stress at yield divided by 2, same as we had before. The shear stress that we calculated previously was 90.1. Yeah, 90.1. So our factor of safety this time is only 2.4. And still safe. The criteria still predicts that we haven't reached yield. So let's have a look at the von Mises criteria. Put our values into the equation for the von Mises stress, and we get 180.2. So here, the von Mises stress is the same value that we got for the maximum stress, right? That's because there's no shear stress in this orientation, right? There is shear stress because we've said it's 90.1, the maximum, right? But in this orientation, there's no shear stress, right? So in that case, the von Mises stress is equal to the maximum principal stress. So if we plot the principal stresses here on our graphical representation of the two criteria, right, it lands here. Stress minimum was 0. Stress maximum was whatever value it was, right, less than the yield stress, and it lands here. Okay. Again, the maximum shear stress is not more, I've cut and paste here, is actually not more conservative. They're the same, right? Because if we increase the loading, it would move out along here. And when we have just a uniaxial state of stress, then at this point, the two curves cross over each other, right? So the green ellipse and the blue hexagon, roughly, at this point is the same for both. All right. So here I go through, from here we go through the circular rod, doing the same thing that we've just done. So I've taken about an hour and a half to go through all of that. So clearly we weren't going to get through more than that in the tutorial. So you can make use of this as extra homework to do, right? And I'll post the solutions for the rest of this as well. But what I will do, just as a sneak peek, is to just skip through here. Right? I don't expect you to follow this as I'm skipping through. I just want to show you something, I think at the end of this. So I'm going to go through this as a solution for you, but I think there's something at the end here I really wanted to demonstrate. So I've just done the more circles. Make sure you go through this for yourself, right, as exercises. So compare. So this example here, what I just wanted to show, I think. No. Okay. All right. Let's go. Sorry. This is really bad. I know. I'm sorry. Let's go back to where we were. Put it on ×2 on the thing here to get ahead. Right. What I just wanted to show you here, if we have a state of stress that let me get my pen. If you have a state of stress that falls out here, right? So we have a maximum stress, maximum principal stress that's a little bit more than half the yield. So let's say 0.6 times the yield stress, and a negative principal stress that's also about 0.6, 0.7 times the yield stress, we fall out here, right? And our failure criteria will predict that the material has yielded at that point, right? So we've got a maximum principal stress, only 0.7 of the yield stress, and yet the criteria says, the failure criteria says that the point has yielded. Okay, so that's why you need to have a failure criterion. You can't just simply say, all right, the maximum principal stress is a value, it's less than the yield stress, therefore it's okay. No, right? Not always. If you're up here, right, if you're in this section, yes. If you've got a state of stress that puts you down here, right, then no, right? Just because the maximum principal stress is less than the yield stress doesn't mean you haven't yielded, right? Anyway, so that's the end of that. I'm going to stop.